we want to do some more problems involving finding out where a function is increasing or decreasing. So we've already done a couple of these problems, but we wanted to see what possibilities there are in these kind of problems. So let's start with problem 24. Here you have a function f of x is equal to 1/4 x to the fourth minus 1/3 x cubed minus x squared. Well, the first thing I want to do, the first thing in our four-step process is to take the derivative. But I do want to reiterate here that it is kind of important in some of the later problems to determine right off the bat what the domain of the function is. So I'm going to go ahead and keep doing that. What is our domain? Well, it is just a polynomial. Polynomials have domain all real numbers. So once again, the domain here isn't too relevant to this particular problem, but we want to be in the habit of finding it every time. Next, we take the derivative. Remember here, we just differentiate these powers. With x to the fourth, we bring down that 4 and reduce the power by 1 to get a 3. But the 4 that we bring down actually cancel out the 1/4. So we actually just get an x cubed. You might be able to see why they picked the 1/4 in front of that. They picked it specifically so we get a nice derivative. Moving on to here, x cubed, we bring down that 3. Of course, it cancels the 1/3, and then the new power is a 2. Finally, here, x squared becomes a 2x. After we find the derivative, now we want to find the critical points. We want to ask, where does the derivative not exist, and where is the derivative equal to 0? Well, it's a polynomial. The derivative always exists here, so we don't have to worry about that part. But we do need to worry about when does the derivative equal 0. And this is a formula that we're going to have to solve. Now, they were nice. They didn't give us a linear term to begin with, so we don't have a constant term in this problem, in this polynomial. So we can go ahead and pull out an x. Everything here has at least one x in it, so we can go ahead and pull out that x. Next, we have a quadratic here that we can factor. Because we just have x squared in front, it's going to be x plus or minus something, and then x plus or minus something. Whatever those two things are, they have to multiply to give us a -2, but they essentially have to add to give us a -1 in the middle. Well, that's going to be a -2 and a +1. When we add those together, we get -1, but when we multiply them, we get -2. Now we have a product of three things equaling 0. That means one of those three things has to equal 0. So our possibilities here, well, of course, x itself could be 0, x could be 2, or x could be a -1. Those are our three possibilities, and those are our critical numbers. I'm going to go ahead and make a number line. On my number line, I'm going to put my three values. Kind of why I put these in order was because they're going to be in order on my number line. And I don't really care what the distance between these points on my number line are. I didn't like here. Technically, the space between 0 and 2 should be twice as big as the space between -1 and 0. But I don't really care about that right now. We're not really concerned with that. The important thing here is that this number line represents 4 different intervals. We have the interval from negative infinity to -1. Sorry about that. That's one interval. Then we have the interval from -1 to 0. Then we have the interval from 0 to 2. And finally, we have the interval from 2 to infinity. We have 4 different sections on this line. Each of those sections, we're going to go ahead and pick a test point in the middle of it, so somewhere in that portion of it. And we're going to take those test points and we're going to plug them into our derivative. Plug them into this formula here. From negative infinity to negative 1, probably just want to pick the smallest integers that we can, or, well, smallest, basically closest to 0. Let me put it that way. I'm going to go ahead and put in negative 2. And remember, I'm putting that into my derivative, not into the original function. So negative 2, when we plug it into here, negative 2 cubed is a negative 8. Negative 2 squared is a positive 4, but I'm subtracting it. Then negative 2 times negative 2 means that we're going to be adding a 4. But overall, we get a negative 8. This is a negative value. So I'm going to put a negative here to show me that it's negative. Basically, for any number, if I pick negative 53 and plugged into f prime, I'm guaranteed at this point that I'm going to get a negative number. I don't have to put that into my derivative to test that. I know it to be true right now, guaranteed. Now, probably the most annoying of these intervals is going to be from negative 1 to 0. There's no integers in this interval, so I'm going to have to pick a fraction. I'm going to go ahead and pick just negative 1/2, because that is a number between negative 1 and 0. If we go through that, x cubed, so negative 1/2 cubed is going to be a negative 1/8. Negative 1/2 squared is going to be a positive 1/4, but we're subtracting it. And finally, negative 2 times negative 1/2 is a positive 1. If we add all these together, we get a 5/8. Specifically, it's a positive 5/8. I don't really care what these values are. I just need to know whether they're positive or negative. But the point here is that from negative 1 to 0, I know that every one of those values in that interval, when plugged into f prime, they give me a positive number. Go ahead and move on from 0 to 2. Of course, there's one integer now. We can go ahead and just plug in 1. That's an easy enough number to use. When I plug 1 into my derivative, I get 1 here, get 1 here, but I get the negative 2 here. So 1 minus 1 minus 2. Of course, when we add all those together, we get negative 2, which is a negative number. We have a negative there. Finally, from 2 to infinity, I'll pick the smallest number I can. I'll just go ahead and pick 3. It's the next integer after 2. When I plug those in, 3 cubed is 27. 3 squared is 9. Then negative 2 times 3 gives me a negative 6. 27 minus 9 minus 6 is a positive 12. So I have a positive here. So I know my derivative is negative here, positive here, negative here, and positive here. That means my function, my original function, is going to be decreasing from negative infinity to negative 1. It's going to be increasing from negative 1 to 0. It's going to be decreasing again from 0 to 2. And it's going to be increasing from 2 onward. And I'm just going to go ahead and list out those intervals. So I'm going to abbreviate it as INC and DEC. So it's increasing from negative infinity to negative 1. Sorry. I want to start with the increase. Increasing is negative 1 to 0. Negative 1 to 0 and 2 to infinity. Those are the intervals where it's increasing. Now, don't put a union sign in here. In some situations, like when you're doing problems with the domain and stuff like that, you'll frequently want to put a union sign between the intervals. We are not doing that here. Just GeoGebra, or not GeoGebra, WebAssign wants you to put your intervals in with a comma between them, because there's reasons why we won't have increasing over multiple intervals at the same time. It's increasing on this one and it's increasing on this one, but those are separate from each other. Same thing with decreasing. It's decreasing from negative infinity to negative 1, and then again from 0 to 2, but not at the same time. And if we go ahead and graph this, maybe you can see why that's going to be true. So remember here, our function is f of x is equal to 1/4 of x to the 4th minus 1/3 of x cubed, and then minus x squared. We have this function here. If we go ahead and put in our critical points, so remember those were at -1, I'm just going to go ahead and put in f of -1. That will give me my y value. Then we have 0, f of 0. Probably can guess what that one is. It's just the origin point. And then we have 2, f of 2. Those are our critical points. Those are the places where it can change from being increasing to decreasing, or vice versa. And we can see that our function is definitely decreasing from -infinity until x becomes -1. It's increasing just a little bit, but it is increasing from -1 to 0. But then it decreases from 0 to 2 and increases from that point forward. But notice that if we were to try to combine, say, the interval from -infinity to -1 with the interval from 0 to 2, there are definitely points in the second interval that are higher than the points in the first interval. Even though the values over here are the x values over here are definitely bigger than the x values over here. If we try to include those two pieces together, we would actually be violating our definition of what decreasing means. It's decreasing down to here, but then it kind of, if we ignore this interval in the middle, it kind of jumps up again. It's no longer decreasing the whole way. It jumps up. So we want to consider them separate intervals, completely separate things. Let's work on another problem. Let's look at problem 32. We're going to stop talking about polynomials, and we're going to have a square root. We have the square root of 9 minus x squared. Now here's where the domain kind of comes into play. What is the domain of this function? Well, remember, we can't have a negative under our square root. So we need 9 minus x squared to be a non-negative number. And that's going to only be true if x squared is not bigger than 9. Our domain here is actually the interval from -3 to 3, because these are all the numbers where x squared is not bigger than 9. It's 9 here, it's 9 here, but in the middle it's smaller. Outside of this interval it's bigger. That means we're only going to be looking at stuff from -3 to 3. We want to ignore everything else. But we do start again with our derivative. Now note here that we do have to deal with the fact that we have a square root. In fact, maybe we want to rewrite our function as a 1/2 power. So we have 9 minus x squared to the 1/2 power. And then we use, I'm going to call it the chain rule. I'm going to stop referring to it as the general power rule and just refer to it as the chain rule at this point. But we're using the chain rule. We're going to bring down that 1/2. We're going to reduce that power by 1. So 1/2 minus 1 gives us a -1/2. But we also have to multiply by the derivative of the inside function. Derivative of 9 minus x squared, well, the 9 goes away, but the minus x squared becomes a minus 2x. I'm also going to go ahead and simplify this form in order to make it easier to work with. Because I am going to have to actually work with my derivative now and not just write the derivative out and just be done with it. First things first, we can go ahead and cancel our 2's. The 2 and the 1/2, they cancel out. We solve a minus x, and we still have this thing to the -1/2 power. But of course, the -1/2 power, the negative there means that we're on the bottom, and the 1/2 means that it's the square root. So we still have the negative x, but now we also have a square root of 9 minus x squared on the bottom. And we're going to be asking ourselves, what are the critical points of this function, or where does this derivative either not exist or equal 0? Well, if a fraction equals 0, basically, if this thing equals 0, that means the top has to equal 0. If we have a non-zero number divided by something, then we're never going to get 0 from that. So the only way this can be true is if the top is equal to 0. Basically, when negative x equals 0. Or in other words, x equals 0. What about the derivative not existing? This essentially is going back to a domain question. What is the domain of this derivative? Well, there's two things here now. Where's the bottom equal to 0, and where is a negative under the square root? Well, if there's a negative under the square root, we weren't in the domain of the original function anyways. We can't have negatives in there anyways because we're only looking at a domain from negative 3 to 3. But we could have the bottom equal to 0. Where is the square root of 9 minus x squared equal to 0? Well, the square root doesn't matter there. If we square both sides, we just have 9 minus x squared equals 0, which just means that x is either plus or minus 3. So in a way, we've gained two critical points from here. There are the endpoints of our domain. If we go ahead and make our number line, this time I'm not actually going to put the arrow here because we actually are never going to go past negative 3 and 3. There's no interval from 3 onward, or no interval from negative 3 downward. Then I'm also going to include x equals 0 as one of my other critical points. So we include all three of our critical points, and we also essentially include the places where things become discontinuous. When the function stops existing at those endpoints, we need to include those. But at this point, all we have to do is plug in test points. So I'm going to go ahead and pick a value between negative 3 and 0 to plug into my derivative. Might as well go ahead and pick negative 1 because I want to pick an integer because it'll be easier to work with. And I only really have two choices. Negative 1 will be the easier of negative 1 and negative 2. I go ahead and plug those into my derivative. Sorry, there should be f prime of negative 1. Negative x on top, so negative and negative 1 is a positive 1. On the bottom, I have the square root of 9 minus 1, negative 1 squared. Negative 1 squared, of course, is 1. 9 minus 1 is 8. So we get 1 over the square root of 8. Now, we don't actually need to know exactly what this value is. All we need to know is that this is a positive number. It is not negative. There's no negatives involved here. Taking the square root and putting it on the bottom does not change this from being positive. So we definitely have a positive value here. We go ahead and look at 1 instead. So looking at between 0 and 3, I'm going to pick a test point of 1. I plug those in. That actually doesn't really change much on the bottom because the square got rid of the negative anyways. But it does leave this negative on top. I'm going to get a negative 1 over the square root of 8, which that is a negative number this time. So we have a negative number here. So we can say that our function is increasing from negative 3 to 0. Now, you could go ahead and just put in the open interval here. Technically, we could also include the endpoint of negative 3, just because there's not really anything below negative 3 to counteract it being increasing. You can do the same thing for the decreasing portion on the other side, from 0 to 3. Or you could say from 0 to 3 including 3. In general, it's pretty safe to just stick with the open intervals. In fact, WebAssign will take either answer on this problem. So unless you're sure of whether or not we can include this in points, just go ahead and use the open intervals. The only reason I'm doing that here is because there's not really anything, there's nothing on the other sides of -3 and 3 to worry about. So there's no reason not to include them. If we go ahead and plot this curve, so f of x is equal to the square root of 9 minus x squared. I have this curve. Now you might recognize this curve. It is actually a semicircle. This is actually part of the circle x squared plus y squared equals 9. But it's only the top half of it. Kind of zoom in on that a little bit. So we definitely have critical points of -3, 0, 3, 0, and 0, 3. Those are points on our curve. It is definitely increasing from x values -3 to 0 and decreasing from 0 to 3. And that's really all there is to say about that, I guess. It's definitely increasing here, it's definitely decreasing there. Next problem, we're going to look at problem 36. Here they call our function h instead of f. That doesn't really change what we're going to do with it, but we'll follow along. We have x times the cube root of x minus 1. So definitely a little bit more complicated of a function. There is not only a root, but we then take the product with x. If we talk about the domain of this function, though, the domain is actually easier because there's no number that we can't plug into here. The cube root does not have the same problem that square roots have. We can have negative numbers under a square root, or under a cube root. Square roots, definitely not. Cube roots, the negative just kind of gets pulled out. So obviously we can plug any number into x, but we can also plug any number into this cube root of x minus 1. So the domain here is all real numbers. If we want to differentiate this, though, first we're going to go ahead and turn the cube root into 1/3 power, because it'll be easier to deal with that now. When we differentiate it, not only are we going to have to use the chain rule for the 1/3 power, but we're also going to have to use the product rule to deal with the x times that. So going through the product rule, we start with the derivative of the first piece. Derivative of x is just 1. So 1 times the other piece. Now we have plus the first piece left alone, we'll just have an x, times the derivative of the second piece. What is the derivative of x minus 1 to the 1/3 power? That's where our chain rule comes in. Well, since we're dealing with a 1/3 power, we're going to bring down that 1/3. I'm going to go ahead and actually put it in front of the x. And then I'm going to reduce the 1/3 by 1. 1/3 minus 1 is a -2/3. Then I need to multiply by the derivative of the inside. But this time the inside is just x minus 1. The derivative of that is 1. So I'm just going to leave that part out. It's just times 1. And now if I want to actually do anything with this, it might be helpful to kind of interpret what this means. The negative here does mean that this is on the bottom. I'm going to go ahead and leave everything else as... I'm going to use the fractional powers, though. But I'm going to go ahead and move this 3 to the bottom and move this to 2/3 to the bottom. So we have two questions because we want to find out where the critical points are. First of all, where does this equal to 0? Where is this thing, which instead of rewriting it again, I'm just going to go ahead and copy it. Where is that equal to 0? Well, if I'm going to do that, it might be nice to not have any fractions. So let's go ahead and multiply both sides of this equation by 3 times x minus 1 to the 2/3 power. So here I'm going to multiply this by 3 times x minus 1 to the 2/3, but remember when I multiply a 1/3 power and a 2/3 power the same thing, I can just add those powers together. Here, multiplying it by 3 times x minus 1 to the 2/3 just gets rid of that bottom. We just get the x. And of course, multiplying 0 by that doesn't matter. It's just 0. But the point here is now I have 3 times this to the, well, 1/3 plus 2/3 is 1. So really just 3 times x minus 1 plus x equals 0. So it's already simplified quite a bit just by the fact that I can combine those to get a 1 power. If I go ahead and combine and work this out now, we have a 3x plus an x is a 4x, but we also have a minus 3. Or in other words, 4x equals 3, or x equals 3/4. So that means 3/4 is going to be a critical point of our function. What about the other side? What about where does the derivative not exist? Since this is basically a domain question for the derivative, we're going to focus on parts that can cause problems. Negatives under the roots don't cause problems here because they are just cube roots. Even the 2/3 here, we don't have to worry about negatives. But we do have to worry about 0 on the bottom of this second term here. Basically, where is x minus 1 to the 2/3 power, or I guess really we should say 3 times that, equals 0. Well, the 3 doesn't really matter. We don't need that part. And in fact, we can even get rid of the 2/3 part. This is only going to equal 0 when x minus 1 equals 0. Or in other words, x equals 1 is another critical point. When x equals 1, we have a problem. Let's go ahead and make another page for this. So we'll have a number line here where we have to include 1, and we also have to include 3/4. Those are our two critical points. We're going to take some test points. So some test point between negative infinity and 3/4. I always like to pick 0 if I can. So I have h prime of 0. So I guess I probably should copy this over. So I have h prime of x is equal to this formula here. When I plug in 0, well, here I get negative 1 to the 1/3 power. Here, well, I have a 0 on top, so that's just 0. And negative 1 to the 3/2 power is just negative 1. We have a negative number here. If we move on to 3/4 to 1, fortunately there we kind of have to deal with fractions. I'm actually just going to go ahead and pick 0.9, and I'm going to use a calculator. I'm going to go ahead and plug 0.9 into this formula, and I get that it's approximately 0.9283. The important point here, though, is that I actually got a positive number. So we get a positive here. Finally, I picked 2 for my test point for 1 to infinity, just because I like to pick integers if I can. But it turns out I still needed to use a calculator for this. I get approximately 1.67989. But the important point, again, is that it's a positive number. I get a plus sign. That means I could write my answer as increasing on 3/4 to 1 and from 1 to infinity, and it's decreasing from negative infinity to 3/4. Now, you might be wondering here, if it's increasing from 3/4 to 1 and increasing from 1 to infinity, why can't I just say it's increasing from 3/4 to infinity? Well, it's sometimes possible to go ahead and combine intervals like that when they're next to each other, but we can't assume that we can always do that. Let's look at the graph of this. So remember, our function here is h of x is equal to x times the cube root of x minus 1, and we get this particular curve here. Now it does have two critical points. Like we said, 1, 0 is a critical point, but also 3/4, comma, whatever the value of the function is at 3/4, which turns out to be like minus 0.47. But we have 2 points on our curve. It is definitely decreasing from negative infinity to 3/4. It increases from 3/4 to 1, and then it increases from 1 to infinity. In this particular case, it doesn't actually change from increasing at 1. It actually does increase from 3/4 all the way to infinity. So we could actually change our answer here. So we could change this to 3/4 to infinity. But we can't always assume that that's true. And I'll show you an example where that isn't true in the next example. But because I don't want this to just kind of go on and on and on, I am going to split this up into a third video, and we'll go through some more examples, some more things that could be a little bit different from what we expect to have happen. So meet me in that one, and we'll go ahead and finish this chapter, or this section, not this chapter. Got a lot more of the chapter to go. So I'll see you in the next video.